Class 11 Chemistry, Chemical Bonding and Molecular Structure. Hello students, this is your Archita ma'am, Chemistry ma'am. Today in this presentation, I am going to discuss the bonding of the molecules and the structure of the molecules. First topic is Lewis dot structure. Lewis postulated that atoms achieve the stable octet when they are linked by chemical bonds. In the formation of a molecule, only the outer shell electrons take part in chemical combination and they are known as valence electrons. These notations are called Lewis symbol. As given in the first half of the slide, lithium is shown by allied dot, beryllium by 2 dots, and so on. The number of dots around the symbol represents the number of valence electrons. This number of valence electrons help to calculate the common or group valence of the element. The bond formed as a result of the electrostatic attraction between the positive and negative ions was termed as the electrovalent bond. The electrovalence is thus equal to the number of unit charge on the ion. Now let us see a new topic, formal charge. Lewis dot structure in general do not represent the actual shapes of the molecules. In case of polyatomic ions, the net charge is possessed by the ion as a whole and not by a particular atom. It is, however, feasible to assign a formal charge on each atom. The formal charge of an atom in a polyatomic molecule or ion may be defined as the difference between the number of valence electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. The formula for the calculation of the formal charge is shown in the slide. Generally, the lowest energy structure is the one with the smallest formal charge on the atom. The formal charge is a factor based on a pure covalent view of bonding in which electron pairs are shared equally by neighboring atoms. Now let us discuss lattice energy. Lattice energy and lattice enthalpy are same. The lattice energy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. The lattice enthalpy of NaCl is 788 kJ per mole. This process involves both the attractive forces between ions of opposite charges and the repulsive force between ions of like charge. The solid crystal, being three-dimensional, is not possible to calculate lattice enthalpy directly from the interaction of forces of attraction and repulsion only. Factors associated with the crystal geometry have to be included. Now we would see the bond parameters. Bond length. It is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. Bond lengths are measured by spectroscopic X-ray diffraction and electron diffraction techniques. Bond angle. It is defined as the angle between the orbitals containing bonding electron pair around the central atom in a molecule or complex ion. Bond angle is expressed in degree, which can be experimentally determined by spectroscopic method. Next is bond enthalpy. It is defined as the amount of energy required to break 1 mole of bond of a particular type between two atoms in a gaseous state. It is important that larger the bond dissociation enthalpy, stronger will be the bond in the molecule. Bond order. In the Lewis description of covalent bond, the bond order is given by the number of bonds between the two atoms in a molecule. Isoelectronic molecules and ions have identical bond orders. For example, F2 and O2 2- have bond order 1. N2, carbonyl and NO+ have bond order 3. A general correlation useful for understanding the stabilities of molecule is that with increase in bond order, bond enthalpy increases and bond length decreases. Polarity. The existence of 100% ionic or covalent bond represents an ideal situation. In reality, no bond or a compound is either completely covalent or ionic. When covalent bond is formed between two similar atoms, for example in H2O2Cl2, N2 and F2, the shared pair of electron is equally attracted by the two atoms. As a result, electron pair is situated exactly between the two identical nuclei. But in case of heteronuclear molecule like HF, the shared electron pair between the two atoms get displaced more towards fluorine, since the electronegativity of fluorine is far greater than that of hydrogen. The resultant covalent bond is a polar covalent bond. Further, dipole moment is a vector quantity and is depicted by a small arrow with tail on the positive center. You just see here. Several examples of this dipole moment is also shown. You see in the slide. For the case of H2, NH3, CCl4, CH2Cl2, these all examples are given. Now we would discuss VSEPR theory. The full form of VSEPR is the valence shell electron pair repulsion theory. As already explained, Lewis concept is unable to explain the shape of the molecule. This theory provides a simple procedure to predict the shape of the covalent molecule. So the main postulates of VSEPR theory are like the shape of a molecule depends upon the number of the valence shell electron pairs around the central atom. pair of electrons in the valence shell repel one another since their electron clouds are negatively charged. These pairs of electrons tends to occupy such position in such that minimize repulsion and thus maximize distance between them. The valence shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from one another. A multiple bond is treated as if it is a single electron pair, and the two or three electron pairs of a multiple bond are treated as a single super pair. In the slide, for different electron pair geometries are given. For the two bonds, one structure geometry is possible. For the three bonds, two structure is possible, that is trigonal, planar and bent. For the four bonds, there could be like three kinds of geometry like tetrahedral, trigonal, pyramidal and bent. For the five bonds, there could be four geometrical structure: trigonal, bipyramidal, sawhorse, T-shaped, linear. For the six bonds, there could be five molecular geometry available, like octahedral, square pyramidal, square planar, T-shaped or linear. Valence bond theory. It is, in shortcut, it is called VBT theory. A covalent bond is formed by the overlapping of two half-filled atomic orbitals of two atoms having electrons with opposite spin. Similar spin electrons would not overlap at all. Some of the postulates of this valence bond theory is shown in the slide. Covalent bonds are formed when two valence orbitals belonging to two different atoms overlap on each other. The electron density in the area between the two bonding atoms increase as a result of this overlapping. The presence of many unpaired electrons in the valence shell of an atom enables it to form multiple bonds with other atoms. The paired electrons present in the valence shell do not participate in the formation of chemical bonds as per the valence bond theory. Covalent chemical bonds are directional and are also parallel to the region corresponding to the atomic orbitals that are overlapping. Sigma bonds and pi bond differ in the pattern that the atomic orbitals overlap. Pi bonds are formed from sideways overlapping, whereas the overlapping along the axis containing the nuclei of the two atoms leads to the formation of sigma bond.